record on computer. So we should have a record on computer. I am not muted and the video is recording. All right. So that being said, we're going to continue where we left off yesterday. So yesterday we talked about the different conformations and how to use a Fisher projection. Fisher projections are looking down two carbon-carbon atoms and then being able to orient the three things attached to each of those two carbon-carbon atoms is important, okay? So you want to practice that on the homework. There are several practice problems on the homework for chapter 4, so you want to make sure to do those. Now, because of our Fisher projection, we saw that the best way to have our substituents organized on our compound is to have them in a staggered configuration and anti, if at all possible. Well, that means that when we look at our zigzag skeletal structure, our zigzag skeletal structure actually has them in their staggered and anti configuration. Okay, so this is technically our lowest energy conformation. Doesn't mean that's how it is all the time. It just means that that's why we draw it in this way, because that's its lowest energy conformation. Okay, so that being said, that doesn't mean that the molecule stays like that at all times, okay? So while we can draw it in this lowest energy conformation here, part of the time it's going to be in some other configuration. It has free rotation around those sigma bonds, okay? So when don't we have free rotation around our sigma bonds? We don't have free rotation around our sigma bonds when we have rings, okay? And the reason we don't have free rotation around that is because we have the two ends of the molecule are being tied together, okay? So if we look at our standard sp3 hybridized orbitals, we're going to have that 109.5 degrees, our tetrahedral structure. Okay, but when we have rings, we can't always get this tetrahedral structure. They're going to try to get that 109.5 degrees, but they're not always going to do that. And because of that, we have what we call ring strain, ring strain. So ring strain is when our sp3 hybridized carbons cannot reach that 109 degrees, okay? And with the smaller you get your ring, the more ring strain it has. So let's look at our smallest ring we can possibly make, which is this one right here, our cyclopropane. Cyclopropane has an angle of about 60 degrees because we have a triangle, and so we can only do a triangle. Okay, which means we have about 49 degrees away from 109 degrees that it wants. So that's an incredible amount of ring strain. So cyclopropane has the highest amount of ring strain. Highest. Okay, then we follow that with the butane. That's only 4 carbons, so it's cyclobutane. And it's got about 19.5 degrees before it's actually going to be happy at 109. And even our cyclopentane, right here, 5, is not at 109.5 degrees. It's about 108 degrees. So there is ring strain in that one as well. But if we have our cyclohexane flat, that's 120 degrees. That's bigger than our 109 degrees. So that means that of these, we have the highest ring strain here, and then it looks like this might be the lowest ring strain, but that's only because we're drawing this flat. It turns out cyclohexane has 2 conformations that let it actually reach that 109.5 degrees. Okay, so let's continue that, and let's look at this in a 3-dimensional sense, okay? Our cyclopropane has to be a flat plane. There's no other way for it to be because of its 3 points make a plane. So what we see is that they have very strange bonds. Those are bent. The overlap between the sp3 hybridized orbitals is not really great. And we call those banana bonds, and that's giving us a lot of strain. Okay, now in cyclobutane, we have a little bit more flexibility, and actually it goes to what we call a pucker. And so it actually is relieving some of the ring strain by moving into this puckered format, but it doesn't relieve all of the ring strain. So it does that to do that. Now, when we have cyclopentane, we end up with 4 of the atoms in the same bond, and one of the atoms gets out of the thing. And we call that the envelope formation. And so it's trying to relieve some ring strain. But notice this is still the highest ring strain, and we're starting to lose the ring strain. We're getting less and less as we get here. But now we have cyclohexane. I want to talk about that on the next slide. But cycloheptane, we have it kind of folded in a kind of weird way, trying to make as much as we can into its thing. And it actually has more ring strain than cyclohexane. And then when we go up to this, we have it again folded in and kind of trying to make as many of the bonds as 120 degrees as 109.5 degrees as possible. But it is still not 100% flat or 100% bent. So what is so special about cyclohexane? Well, it turns out cyclohexane, if we draw it flat, all of the hydrogens would be eclipsed with each other, and all of the carbons would also be eclipsed with each other. But that's not what it does. It can actually bend a little bit and get into a puckered chair conformation to eliminate all of that strain. Because when it does this, our hydrogens are now staggered from each other, and our carbons attached here are in a gauche position here. So if we were to draw a Newman projection down this bond here, we would see that the front carbon has the CH2. It has a hydrogen here and a hydrogen here. That's this carbon. And then if we were to draw the second carbon behind it, we have a hydrogen up, we have a hydrogen over here, and we have a CH2 in that gauche position. Okay, so it's in a staggered conformation, and it's in a gauche conformation. So that means we're eliminating as much of the intramolecular strain as possible in this chair conformation. In fact, if you were to draw the Newman projection down every single one of these bonds, you would see that they all form this configuration. It would be a gauche configuration, and it would be staggered. Okay, that's why in our chair position, we actually have no ring strain, 0 ring strain. Okay, so that means that if we go back to the other side here, we have ring strain goes down to 0 here, and then it goes up here because not all of those bonds can be in a gauche conformation. Okay, so cyclohexane is unique in the fact that it has 0 ring strain below cyclohexane, ring strain above cyclohexane. All right, so let's take a minute and talk about what we call chair conformation. So if we look at it here, and I'm going to draw it a little bit differently right here. So here's the back of the chair, here's the foot of the chair, and here's the seat of the chair. That's why we call it the chair conformation. Okay, so I'm going to teach you a really quick way to be able to draw a chair conformation. Okay, it's not that hard. It just takes a little bit of practice. So what you want to do is you want to draw parallel line, and then you want to draw a parallel line, and then you want to connect them, parallel line. So if you draw 2 lines, and then 2 lines, you can make a cyclohexane in the chair conformation. Okay, so that being said, let's go ahead and look at that gauche conformation again. Okay, so what we're going to look at in this particular slide is the fact that we're going to do our Newman projection down this bond, and then we're going to do also our Newman projection around that bond. So that means that our 2 centers, one is up, this one, and one is down, this one. Those are our bridging carbons. Okay, so our bridging carbons will bridge our Newman projection on one side and our Newman projection on the other side. And so what this gives us is our totally staggered conformation, but our 2 bridges are in their Gauss conformation. And again, you can go around and draw it through all the other sets, all opposing bonds in your cyclohexane will give you this exact same Newman projection. It's just your bridging carbons will be up or down. So they'll alternate between being above in the front and below in the front. Okay, this is why we have 0 ring strain in there, because all of our carbons are at 109.5 degrees. Okay, now that being said, we have 2 different conformations for our hydrogens in the middle. Okay, and what we see here is that we have hydrogens that are easier to see here as sticking up, and in fact, one of the hydrogens here is actually sticking up. All of these are going to be parallel with each other. And then we have a second kind of hydrogen. These are sticking out. Okay. And so there's going to be one of these that's sticking out, one of these that's sticking out. And we're going to see that they have 2 different conformations. The ones sticking up in parallel have a name. The ones sticking out and all kind of in a kind of crisscross pattern are going to have a separate name. Okay. The one sticking up, we want to call axial. Now, the way to think about that is if we draw a axis on here. So let's say this is a planet, okay? So this is Earth, and we're going to have an axis, and it's going to rotate around this axis, right? All the axial hydrogens are going to be parallel with the axis of the Earth. Okay, they're all parallel. See how they're all pointing straight up and straight down. Okay, now the other hydrogens are around the equator, and they're all pointing up or down around the equator. So we call those equatorial hydrogens. Okay, so axials are up or down, equatorials are facing out. Okay, so it's really easy to pay attention to this because in the chair conformation, you're always going to have 3 up axials, you're going to have 3 down axials, you're going to have 3 outward up equatorials, and 3 outward down equatorials. Okay, because the way we've drawn this, they're always going to be in that way. Okay, so the other cool thing about this right here is now that we have our axials and our equatorials, if we were to go ahead and, oh, no, I'm going to save that for another slide. All right, so that's not the only conformation our cyclohexane can be in. Our chair conformation is our lowest energy conformation. It has no ring strain. Okay, but we have to going from one form of the chair to the other form of the chair, we can go through what we call the boat configuration. So in the boat configuration, we have just one bond. This carbon right here is going to flip up. And when we do that, we have now this carbon is the flipped up carbon. This one is staying exactly where it was, and it's still flipped up. So now it's a boat. So now we can think of it as the 2 ends of the boat. It's like a Viking ship, you know, where we have those are there. Now, if all we did was move the second carbon down, we get now to the second chair form. Okay, so we can go from one chair to the other chair. One chair form has 0 ring strain. One chair form has 0 ring strain. Okay, now the boat conformation has no angle strain, but if we drew the Newman projection, we would see we are now in the eclipsed form. So when we take this right here, and we're going to draw our Newman projection through this bond and through this bond here. So I'm going to say this is the one in the back, and this is the one in the front. Okay, so we've taken that chair position, we've taken that boat position, we've rotated it 90 degrees, and we're looking down the blue axis here and the red axis here. We see that both of the CH2s are eclipsed. The hydrogens are eclipsed, the hydrogens are eclipsed, the hydrogens are eclipsed, and the hydrogens are eclipsed. So what does that mean? We don't have angle strain, but we do have eclipsed strain, which means that our eclipsed form is more takes more energy than our chair form. Our chair form had perfectly staggered gauche. Now we have in our boat form a perfectly eclipsed form. And in our perfectly eclipsed form, we have what we call a steric interaction, but no ring strain. So it's less stable. So it wants to flip from the chair form through the boat form to the other chair form. And so flipping back and forth between the chair forms, it really prefers to do that. But again, we're not adding ring strain. We're only adding interactions through space. Now, we also have another problem when we have our boat here. And we have a problem because this hydrogen and this hydrogen are very close together. Okay, let's think about that as a boat again, like a Viking boat. And if you had a flagpole on one of the Viking boat and a flagpole on the other of the Viking boat, those two hydrogens are going to be those flagpole hydrogens. Okay, and because they're pretty close to each other compared to in the chair position, where they would be very far apart, they are very close to each other. They bump up against each other, and that's giving us steric strain, not angle strain, steric strain. And so those have a special name. We call those flagpole positions. Okay, so the boat conformation does not have axial or equatorial. It has flagpole. Okay, questions on that? Chat is open. I have my mic on. I have my speakers on, so you can talk if you want. We're up to 15 participants. That's great. All right. So what does that mean? So in that Newman projection, we were looking at the energy of rotating around, okay? We can look at that same kind of change in energy as we move through the different molecules, different molecular shapes. Again, we're not breaking bonds. All we're doing is moving from one position to the next position. So if we look at our chair conformation, and this is our chair one, notice that this one's down and this one's up, okay? So we're gonna keep that same orientation. So as we move from our chair to our chair two, we're going to, the first thing we're gonna do is we're gonna move that one side up until it's flat, okay? Why is that so much energy? Well, 1, 2, 3, 4, 5 carbons are now all in the eclipsed formation. So those five carbons are all in the eclipsed formation, and therefore it's a very high energy here. Now, if we take that and rotate this bond up and this bond down to give us our twist boat, we're going to save energy because we're now not eclipsed. We're now partially gauche and partially eclipsed, so we don't have to worry about that much. So we get a savings of energy in this twist boat configuration. Then we go back to our boat conformation. Remember, we have our axial, our flag boat hydrogens right here are giving us strain because of the flag pole thing. And then all we're going to do is we're going to rotate this up and rotate this down, and we're going to get to a twist again. And notice both of those twists are the same energy, okay? Because all we've done is taken it from one side up to one side down, and so we've rotated it. Now, this is that hydrogen that was down way over here. I'm sorry, the carbon that was down over here, and this is the carbon that was up. The carbon that was up is now in the plane of the four other carbons, and therefore it's the highest energy. They're all eclipsed. We have 5 eclipsed hydrogens giving us here, and then this one ends up down, and this one ends up up. And so we've completed from chair 1, where the green carbon is down and the red carbon's up, to chair 2, where the green carbon is up and the red carbon is down. Okay. Do we see why there's a massive energy change as we go through all these things? Okay, and it's best described using our Newman projections. We're seeing that they are fully eclipsed and they are staggered in each of these different conformations. Okay, questions on that? All right, that being said, let's move on to what if you have a substituent, okay? So if you have a substituent, no matter how big your substituent is, it's always going to be more stable in an equatorial, around the outside position than in an axial position. Why? Okay. So when we look at our chair conformation here, and we have our hydrogen here, and our hydrogen here, and our hydrogen here, those are all in the axial position. All three of those are in the axial position, okay? And they're small, but see, they can see each other with electron-electron repulsion, okay? Now, when we put a substituent on here, the substituent is almost always larger than hydrogen. If it's larger than hydrogen, so this electronic cloud is bigger, it's going to start seeing the other hydrogen sooner, and therefore it's going to be less stable. Electron-electron repulsion is going to make it less stable, a higher energy conformation. Okay, so that being said, our chair would want to, this is our, let's call this our chair 1. It's going to want to flip to our chair 2 so that the substituent is lying on the outsides of the system. That makes it further away from all the other substituents, in this case, hydrogen. Okay, so does it vary by size? Yes, it does vary by size. Okay, so in this case here, what we're going to say is that in our equilibrium between having our substituent go from chair 1, which is going to have our hydrogen start in axial, and it's going to convert to chair 2. When it converts to chair 2, that converts it to an equatorial. That's the cool thing. Whenever you go from chair 1, all the axials become equatorials and all the equatorials become axials. Okay, so now let's look at changing the size. Okay, so in this case here, we have an equilibrium of 1 for hydrogen, meaning that for every molecule that's has that hydrogen in the axial position, there's another molecule that has it in the equatorial position. Okay, so what does that mean? When we put a methyl group there, that means that for every molecule that has that methyl group as an axial position, there are 18 more that have it in the equatorial position. So it's 18 times more likely to be in that equatorial position because of its size than having it at the axial position. And then if we get even bigger, this isopropyl group right here, 30 times more, it'll be in the equatorial position than in the axial position. And if we get really big, this is our T-butyl group, right? This is our isopropyl group. Isopropyl, and this is our tert-butyl group here. That's really big, which means for every one of those cyclohexanes with a T-butyl group in the axial position, there are going to be 4,800 of them with that T-butyl in the equatorial position. So it's highly favored to have the big group in the equatorial position. Now, if we have slightly larger than hydrogen, but not necessarily as big as these other groups here, there's still a favorite to be in that equatorial position. For every 14 of those, or let's see, for every 14 in, or every 10 in the axial, they're going to be 14 in the equatorial. So there's a slight favor, but notice that because they're such smaller size, they're not much bigger than hydrogen, that it's not as big or as much of it going to the equatorial side. Okay, so that being said, we can actually count what the percentage is. And so in the case here, we can interpret this as in the ethyl group configuration. Let me circle that in a different color here. In this ethyl group configuration, we have 21 times it's going to be in the equatorial position. Okay, but there's a total of 1 in the axial for every 21 in the equatorial. So that's going to be 1 in axial plus the 21 equatorial equals the total number of chair conformations, which means that if we do our percentages here, 95.95% of the time, that ethyl group is going to be in the equatorial position. And if we do the math for our butyl here, it's going to be 99.98% of the time. Okay, so it's just showing you that that's so much more favored because of that steric interaction. Okay, not ring strain. Ring strain is all about the conformation of the ring, chair 1, chair 2. And then we have conformation with sterics, gives us our substituent wanting to be in the equatorial position. Okay, so what if we have two things on our cyclohexane? Well, if they are the same size, then we have to worry about whether or not the particular isomer we have is going to allow us to have them both be in one position or the other. Okay, so let's go back to remembering what a cis and trans isomer is for a ring. Remember, a cis isomer is having both of the substituents on the same plane, the same side of the ring. A trans isomer is having them on opposite sides of the ring. So if we were to draw a plane right here in the cyclohexane, we see that both of these methyl groups are on the same side. Okay, that means it's the cis isomer. Okay, now when we have this cis isomer here, in our chair 1, we have one in the equatorial position and one in an axial position. So that's chair 1. So in chair 2, we have the axial position turns into the equatorial position. And in chair 2, the equatorial position turns into the axial position. Okay, so what does that mean? Well, in our cis isomer, one has an equatorial and one has an axial, and we flip it to the chair 2, one's axial and one's equatorial. So that means they're the same energy going back and forth and back and forth. Okay, because they are both going to be either in the axial or the equatorial position, depending on which chair we're in. But if we change our isomer, let's look at here, and we're going to draw our line here again. This is our plane right here. We have this methyl group on this side and this methyl group on this side. So now we have a different isomer. We have those two methyl groups on different isomers, and therefore we have our trans isomer. Okay, when we have our trans isomer and we have it in our first position here, we have it in an equatorial and an equatorial. So this is our chair 1. And if we flip it, our equatorials become axials and our axials become equatorials, which means both of these equatorials now become axials. Okay, so which is more stable? Okay, the one where both of your groups are in the equatorial position is going to be more stable than in the axial position because of steric strain. Notice if we drew our Newman projections, they would all be staggered. It's not anything about ring strain, it's everything about steric strain. Okay, so let's extend that right here. So what if you have two different size groups? Okay, in this case here, we have a cis isomer, because if we draw our line through our thing here, we have a T-butyl group and a methyl group on the same side of the ring. So we have our cis isomer right here. Now we have a difference in size. Our methyl group is different in size than our T-butyl group. Okay, but in the case of our cis isomer, both the methyl group and our T-butyl group are in the equatorial position in this chair 1. And notice they have two hydrogens in our axial position. Now, if we were to flip those hydrogens to be in the equatorial position, both the T-butyl group and the methyl group are now in the axial positions, and these are now in our equatorial positions. That means that those two large groups are going to butt up against each other, and they are going to be less stable. So in our cis configuration right here, it is more stable for both of the groups to be in the equatorial position. But what if we had the other isomer? Okay, so now let's look at this. We have, we're going to draw our plane right through here again. And we're going to say, oh, we have a methyl group down and we have our T-butyl group up. So this is our trans isomer. And in our trans isomer, we have a difference in size. Okay, now the T-butyl group is much, much bigger than the much bigger than the methyl group here, which means we want the T-butyl group to be in the axial position. No, that's not right. We want the T-butyl group to be in the equatorial position. The equatorial position is going to be the lowest energy position for it. And this methyl group, which is smaller, can be in the axial position. Okay. Now, if we were to go from ring one, chair one to chair two, we would end up with the formerly equatorial T-butyl group to being axial, and that's less stable. Even though the methyl group here is now in the more stable equatorial position, the T-butyl group is bigger, which means we're going to be favoring the T-butyl group on the equatorial position. All right, questions on that? Okay, so let's talk about the last things we can do with, we're going to close out chapter 4 with the reactions of alkanes. All right, alkanes don't do much because we have a non-polar carbon-carbon bond and a non-polar carbon-hydrogen bond. Okay, that being said, one of the few things they do is burn. And so we can take our non-polar bond and create a more stable polar bond by burning it, okay? And that creates CO2 and water and releases heat, okay? So that means that the carbon-oxygen double bond is actually more stable than the carbon-hydrogen bond because it releases heat during the reaction. We're going to talk about that again in chapter 6. Okay, the only other thing it's going to do here is we're going to talk about this in chapter 10. And this is what we call a radical reaction, okay? A radical reaction only involves single electrons, so we don't have to have a polar bond, okay? And we'll go into the details of this reaction right here in our chapter 10. But I want to show you that it's not because it's a polar bond. We're actually using single electrons to activate the bond there. And that's why it works. Okay, so how do we make alkanes? Well, we can either make alkanes. Well, most of the time we just dig them out of the ground and purify them from fossil fuels. But sometimes we dig stuff out of the ground that has double bonds or triple bonds. And if we have double bonds or triple bonds, we can take those double bonds and add hydrogen across. Remember, there's 4 reactions we can do. We can do substitution reactions, addition reactions, where we add something across a bond. We can do elimination reactions where we create double bonds or triple bonds, and we can rearrange. So this is one of those 4 reactions we can do. We're going to add hydrogen across a double bond. And we do that with a catalyst. Why? It's a nonpolar bond. We have to activate it somehow. It doesn't do much. So what we're going to do is we're going to activate that bond with a catalyst, and we're going to make this double bond. In this case, it is our, we're going to call it our electronucleophile. Okay, why are we going to call it a nucleophile? Because we have 2 electrons in that double bond, okay? So we're going to take that and we're going to add hydrogen to this side and this side at the same time, and we get our alkane. Okay. We can do that with any number of pi bonds. So in the case of 2 pi bonds in an alkyne, all we have to do is add 2 equivalents of hydrogen, 1 across the first pi bond, 1 across the second pi bond. Okay, so we'll see that this is one of the few reactions we can do. Here we have our methyl propene, or it's also called isobutane, but we can add hydrogen across this double bond, and we're going to get to this compound. So this is isobutane. This would be isobutene because it has an ENE. It has a double bond. Okay, we can do that with cyclos here, and we can selectively do it where we are not going to react this other pi bond, we can selectively hit just these pi bonds to reduce them down using this same kind of system. Notice in all these systems, we have a metal catalyst, platinum, palladium, or nickel, and we have hydrogen. We have to activate the hydrogen, we have to activate the double bond to make it react. Okay, we're going to do more of this in chapter 7. Okay, now the last thing we need to talk about in this chapter is what we call degrees of unsaturation, or the index of hydrogen deficiency. What this means is we need to calculate between the number of carbons we have and the number of hydrogens we have. Okay, that's going to tell us how many pi bonds we have or rings we have. Okay, remember in our hydrocarbon, if we look at our general form, it's going to be carbon N, 2N plus 2 is a straight chain alkane. Carbon N, okay, let me write that down. Carbon N, H2N plus 2 is our straight chain alkanes. Okay, carbon N, NH2 is our rings. Okay, because we had to lose those 2 hydrogens to bring it into a ring. So now, by being able to look at our empirical formula for any carbon-hydrogen compound, we can tell how many rings or how many double bonds we have. And so that's called the degree of unsaturation. So that's saying that we can add more hydrogen to it to make it a saturated hydrocarbon. So that means we can just keep adding hydrogen, adding hydrogen, adding hydrogen until it absorbs all it can. Okay, so we have a formula for that. So let's look at the formula. Okay, so if this is our generalized form for a saturated hydrocarbon, we're going to try to figure out how many degrees of unsaturation we have by doing a similar calculation. So we're going to have Cn, that looks familiar, H2N plus 2, that would be a saturated hydrocarbon, minus 2x. Okay, so X is going to be our degree of unsaturation. The reason there's a 2 there is you usually have 2 hydrogens. Notice we added 2 hydrogens for a straight chain, and we removed 2 hydrogens for a ring. So the X is going to be how many things we can add. Okay, so that is going to be the beginning. So let's look at these compounds here, and using this equation. Again, you're going to have to memorize this equation. We only do like 4 equations in organic chemistry, and this is one of them. So you're going to have to do it. All right, so we have this right here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. So that means our N is equal to 10. Okay, and here we have 1 hydrogen, 2 hydrogen, 3 hydrogen, 4 hydrogen, 5 hydrogen, 6 hydrogen, 7, 8, 9, 10. That's 4 bonds there, 11, 12, 13, 14, 15, 16. So we have our hydrogens is equal to 16, okay? So let's do our calculation here. So that means that our Cn H2N plus 2 minus 2x is equal to 16. And our N is equal to 10. All right, so that means we have, in a fully saturated hydrocarbon, we should have 2 times 10 plus 2 hydrogens. Okay, so let's do our calculation here. Okay, and what we'll see is we have 2N plus 2 minus 2x is equal to the number of hydrogens we see in our compound. In this case, it was 16. And our N is 10 because that's how many carbons we have. So we're going to put a 10 there. So that makes this thing 20. So I'm going to redraw this as 20. 20 plus 2 minus 2x is equal to 16. Okay. So let's see, we need to continue that math. So we're going to continue that math. So it's going to be 22 minus 2x is equal to 16. So we have minus 2x is equal to 16 minus 22, because we're just moving it to the other side, algebra. And then we're going to divide both sides by minus, well, okay, let's do the math first. Minus 2x is equal to 16 minus that, which is 4, 5, 6. So we're going to divide both sides by minus 2. So we're going to get it, x is equal to, oh, I'm sorry, that's a minus 6 because 16 is smaller than 22. So that means x is equal to 3. Okay, so that's doing the math, okay, on that compound above. Now, what's the other way to do it? There's a faster way to do it. Count up the number of rings or number of double bonds you have, and that should be exactly the same as your index of hydrogen deficiency. So in this case here, we have one double bond, we have one ring, and we have one double bond. So our hydrogen deficiency should be 3. Okay. Now, we did the math, and it was also 3. So that means it worked. Okay. Let's try 2 more of those, and we'll get it down really packed. And then we have a couple rules. Don't think this is all. We have a couple rules that we need to play with as well. Okay, so our math turned out to be 3. And if we look at the structure, it's 3. Again, let's look at the structure here, and we're going to say 2 rings. So our x should be 2. 2 double bonds, our x should be 2. A ring and a double bond, our x should be 2. Let's double check. Okay, so this is our formula for this one right here. We have 6 hydrogens and 4 carbons. Okay, so that means our N is 4. 4 carbons, N. Okay, so that means our 2N goes to be a total of 8 plus 2 gives us 10. Then we have minus 2x. We are looking for x. We can't do x. And our 6 is the 6 at the other end of the equation. Our hydrogens are at the other end of the equation. That's where this 6 comes from, right here. So it's not, we're going to do that. So now we have our 10. We're going to subtract 10 from both sides to give us minus 10 on this side and minus 10 on this side, and to get rid of the 10. So we have the minus 2x by itself. And that's going to give us minus 4 and a minus 2x. And so if you divide both sides by minus 2, we end up with an x equals 2. Okay, so does that make sense? Thumbs up, anybody want to talk? Okay, so let's do that same thing for benzene, okay? We can look at benzene right here, which is this structure here. That's C6H6, okay? Now, right away, we can either count or we can do the math. And we're going to do both. But we're going to have a double bond, double bond, double bond, and a ring. So our number, our x should be 4. Okay, let's double check. Our n is 6. So this is 6. And our h is 6. So this is 6. Okay, so that means 6 times 2 plus 2 is equal to 14. 12 plus 2 is equal to 14. Then we're looking for x, and our 6 is the number of hydrogens we have. So we're going to subtract 14 from both sides. Okay, so 6 minus 14 is equal to minus 8. And then we have minus 2x on this side. And now we divide both sides by minus 2 to give us our x. And our x ends up being 4. Now, when we drew the structure out, we said 1 double bond, 1 double bond, 1 double bond plus a ring equals 4. Okay, so you can use the equation or the looking at the double bond. You have to use the equation if you have anything other than carbon and hydrogen. Okay, so that's where our rule comes in. In our rule, we have to worry about other atoms, our heteroatoms. Heteroatoms are anything other than carbon and hydrogen. And what we have to look at is how many times they bond. Okay, oxygen bonds 2 times, so we can ignore it. We don't care. Okay, halogens count as hydrogen because they only bond once to carbon, right? Hydrogen bonds once to carbon, halogens bond once to carbon, so they count the same. Okay, so we ignore oxygen. Halogens count as hydrogens, but nitrogen we have to subtract 1. Why? Nitrogen bonds 3 times and has a lone pair. So there's an extra hydrogen there. So we have to remove that hydrogen to account for its being bonded 3 times. Okay, so that means that we can take any set of atoms and turn them into a simplified just carbons and hydrogens. So let's look at this right here. So oxygen, we don't worry about it. It counts as 0. Chlorine, we have to say +3 to the hydrogens. So we have 13, okay? 13 hydrogens. But we have a nitrogen here, so we have to -1. So that means we have 12 hydrogens. So our simplified form now is C6H12. And when we look at our C6H12 and run our math, we can see how it works, okay? So let's do that again with another example with just bromine on here. Remember, bromine is a halogen that only bonds to carbon once, so it counts as a hydrogen. So that turns its formula into C7H12. Our 7 is our N. Our 12 is on the other end of the equation, and we're looking for X. So that gives us 16 minus 2X is equal to 12. And if we divide both sides by 2, we get an X is equal to 2. That means there's 1 ring, 2 rings, 1 double bond and a ring, or 2 double bonds. Okay, that's what X means. We have any of those are possible in our system. Okay, let's do it one more time with N here. We have a nitrogen. So nitrogen, we have to subtract 1 from our system because nitrogen bonds 3 times, which takes our 5 is the same, our N is the same, but our hydrogen goes from 9 to 8 because we had to subtract 1. So that gives us our N is whatever our carbon is, our number on this side is whatever our reduced hydrogen number is, our calculated hydrogen number. And we're going to end up with N is equal to 5. And so we're going to end up with the same thing. X is equal to 2. That means there are 2 double bonds or 2 rings or 1 double bond and 1 ring. Okay, that's what hydrogen deficiency means. The degree of unsaturation of a molecule can be decided in this fashion. Questions on that? Okay, so what we're going to do is we're going to go ahead and take a break. I'm going to email out our chiral activity here in a second, and then we're going to move on to chapter 5, chirality. Okay, let me go ahead and pause the video and Zoom recording. There we go. We should get through chapter 5 today, and unfortunately that means we'll have our chiral activity today as well. And we'll have our exam online tomorrow. It'll be online. Look under Canvas, Quizzes, Exam 2. Okay. Canvas, Quizzes, Exam 2. And then that'll be automatically graded. And so we'll take that, and then I'm going to curve those grades if it's too far off. Our actual first exam was really close to me wearing a kilt. It was 72.5. was the raw score. So we're getting really close to making me wear a kilt. So I think you should get that little extra 2.5 more points there, and we can actually get me to wear a kilt to class. Okay. So that being said, hopefully I will be back live in person on Monday, but it's looking like that might be true. So we'll see. The antivirals are really, really painful now. Anyway, all right. So let's get back into our thing. We have 14 participants. Somebody just dropped out. But what we're going to do is I'm going to do the first half of this, and then I'm going to introduce the chiral activity to you. There's a second page on that chiral activity. Do not do the second page. Only do the first page. Only do the R and S activity on the first half of that. We'll be doing the other half next. Okay. So we'll be doing that by the end of the lecture. Okay. So stereochemistry. Okay, this is what gives people trouble. It's not hard, but it's like Minecraft. You have to be able to rotate things in your head. Okay, so that's the key here, is think about Minecraft or look at models to do this rotating stuff in your head. Okay, so why is it important? Well, it turns out most molecules, in fact, 65% of our pharmaceuticals have a stereoisomer. Remember, stereo is in space isomer, so it's just how they're related in space. About 61 to 62% of all pharmaceuticals use only one of the two isomers. Only one of the two isomers can be active in the body because the body's very selective about how it does. But that doesn't mean that they only make one or the other in nature. In fact, if we look at this here, this is a compound right here called carbone. Carbone can be made in two possible isomers. One is the R isomer, and we'll talk about that, and one is the S isomer, okay? So they're exactly the same except for this placement of this bond in space. One's coming out at us, one's going away from us, okay? So we're looking at just that one bond in space. And what does that mean? Well, our body interprets the one isomer here as having a kind of earthy tone. Caraway seeds are kind of an earthy tone used in rye bread. But the other isomer, our body interprets as spearmint, a minty flavor, okay? So our body can tell the difference just by that one group being changed in space. Okay, so we need to know the difference between these because it gives us more precision in our ability to identify chemicals. All right, so let's talk about isomers. Okay, we talked about elemental isomers are the ones that have different carbons and isotopes. Our isotopes have different different number of neutrons, right? These are isomers. Isomers are different types of chemical compounds. We have a couple different kinds. We have constitutional isomers, which means that they are hooked together differently, okay? They have different IUPAC names, they have different physical properties, they can have different functional groups. So those are constitutional isomers. The empirical formula is the same, but the way they're hooked together is different. Now, the other isomer we have is stereoisomer, meaning they have the same empirical formula and they're hooked together exactly the same way, except for one or more bonds that is changed in space, okay? Which means they are going to have identical IUPAC names except for our prefix of cis or trans in the case of a double bond, or R and S in the case of our sp3 hybridized carbons. Okay, they always have the same functional group. They only differ in their 3D arrangement. Okay, three-dimensional arrangement. So stereo means space, how they're hooked together in space. Constitutional isomers can be really, really different. Stereoisomers only vary in one way, how they look in space. All right, so what does that mean? We have a couple different isomers in stereoisomers, okay? We have, the first thing we have is our double bonds. Our double bonds are what we call geometric isomers because their geometry is different. And we saw that if both groups are on the same side, it's the cis isomer, and both groups are on opposite sides of the double bond, it's the trans isomer. Okay, now this little atom should be more over here, but you get the idea. So we have our cis is on the same side, our trans is on the opposite side. Okay, these are geometric isomers because we have a cis and trans element, but they are still stereoisomers. They're still different in space. All the other connections are the same. The next kind we have are what we call optical isomers. The only way we can tell them apart is through a type of optical measurement. In the case of optical isomers, we have one bond, at least one bond, is different in space. So this atom here is on this side of the molecule, on this side, and it's on the other side of the molecule here. Same melting point, same boiling point, same empirical structure. Everything is exactly the same, except that we can tell them apart using light. That makes them optical isomers. Okay, so let's look at the difference between our constitutional and stereoisomers. Notice this has the same empirical formula. And the only difference is this methyl group is moved from the 2-carbon to the 3-carbon. That being said, they have different names. One is 2-methylpentane, one is 3-methylpentane. Therefore, they are constitutional isomers. Okay, now let's look at our next example here. We have these methyl groups on the same side of the ring, and this methyl group up, this methyl group down, meaning they're on opposite sides of the ring. So now the only difference between them is how they are looked at in space, which means the name is still 1,2-dimethylcyclopentane, but to definitively say which one we have to say cis if they're both on the same side of the ring, and trans if they're on opposite sides of the ring. So that's the difference between a constitutional isomer and a stereoisomer. All right, so now I want to talk to a concept called chirality. Chirality is actually a very old word. It's Greek. It means handedness. Handedness. Okay, so what it's saying is that if you have two hands, not everybody does, but if you do, you have chirality, because this hand is the mirror image of this hand. But if you try to put them overlapping together in the same orientation, with both of the backs facing you and the fronts facing me, they do not overlap. They are not superimposable. They look different. Okay. They have mirror images of each other, but are non-superimposable. That's what chiral means. Chiral means anything that is non-superimposable mirror image of itself. Okay, so if we look at things like that, we have things like our hands here. Because again, if they're in the same orientation, you have finger and thumb, finger, 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 and finger and thumb. So they are different. Okay. But anything that's not a chiral object, that does not have a non-superimposable mirror image, and a mirror image that can be superimposed, we call that achiral or non-chiral. Okay, so imagine you had a chair here. You could perfectly overlap that chair on that one, or this fork on that, and it would look the same. But look at this here. We have in this car here, because we have the steering wheel on one side, the mirror image would have it on the other side. And therefore, when we tried to overlap them, the steering wheel will be on opposite sides of the system. That's why it's a chiral object. All right, so do all molecules have chirality? No, not most molecules aren't. So, but we have to look for the two things. Number one, we look for a mirror image, and then we look, can we overlap them together? Okay, so if we look at water here, we can draw a mirror image of water with hydrogen, hydrogen, oxygen, oxygen, hydrogen, hydrogen. And then if we move this water molecule over here, they are superimposable. They look identical. Oxygens line up with oxygens, hydrogens line up with hydrogens. That means water is achiral, not chiral. Excuse me. All right, so now, so most of the time we're going to look at things that are chiral, have sp3 hybridized orbitals, meaning they're tetrahedrons. Okay, are all tetrahedrons chiral? No, because it's all about the attachment. So let's draw the mirror image of this. So we're going to draw the chlorine on the same side of the chlorine, the bromine on the same side of the bromine, the hydrogen up, and this hydrogen back. Okay, but if we were to take this, rotate this around 180 degrees, the chlorines would line up, the bromines would line up, the hydrogens would line up, the carbons would line up, and the other hydrogens line up, meaning that they are fully superimposable. Okay, so what we're looking for is mirror image, and that at least two of the atoms don't line up with the other molecule to be chiral. If they do line up, they are not chiral. All right, so let's look at these two molecules here. We have a CH3 here, an OH here, an H here, and a CH2CH3. Okay, so that's an ethyl group, right? Now, if we were to think about trying to draw a mirror image, the first thing we would do is we draw a mirror plane, and we'd say, okay, CH3 is going to be here, OH is going to be here. Notice that OH here is kind of pointing out at us in this perspective, so we want to keep it pointing out at us. The hydrogen's kind of pointing back, so we're going to keep that pointing back, and the CH2 is on this side here. Okay, so now we've made a mirror image, okay? But if we were to take the this one here and just try to move it in front of this one over here. So our OHs are aligned, our H's are aligned, and our carbons are aligned. So we get 3 of those atoms do align, and they are in the same place. But the CH3 and the CH2CH3 are not aligned, and these are the opposite on this other side. Okay, this is what we mean by non-superimposable. We're always going to have 3 of the atoms of the compound align, but we're going to have 2 of the other atoms be flipped by it. So what does this mean? Means that to have a chiral carbon, you must have 4 different things attached to your chiral carbon. So that's the first thing we're going to look for. Are there 4 different things attached to a carbon? All right. So anytime we have chirality, we have what we call an asymmetric center or a non-symmetric center. Okay, so that could be a chiral center, a stereogenic center, a stereocenter, a stereocarbon, a chiral carbon. All of those words mean the exact same thing, but they all have the same thing involved. They have a tetrahedral atom, doesn't have to be carbon. They have a tetrahedral atom with 4 different groups. That's the first requirement for chirality. Okay, so can you pick that out of a system? Well, you should be able to, because if we look at our condensed form here, we have 3 carbons on this side, we have 4 carbons on that side, we have an OH here, and we have a hydrogen here. 4 different groups, that's a chiral carbon. We have a CH3 here, we have a CH2CH3 here, we have a bromine and a hydrogen, 4 different groups, it's a chiral carbon. So here we have a CH2, here we have an isopropyl group, here we have a methyl group and a hydrogen, it's a chiral carbon. But this carbon has 2 methyl groups on it. Those are not different. It is not a chiral carbon. Okay, so count the number of different groups you have, and that's the first requirement for chirality. The second requirement is that it must have a non-superimposable mirror image. Okay, so let's talk about that. If a molecule has a non-superimposable mirror image, then it has enantiomers. One is the one enantiomer, and then its non-superimposable mirror image is the other enantiomer. If you can't overlap them, they are not chiral. Okay, so let's look at this compound here. And again, what we're going to do is we're going to draw a mirror here. We're going to say, okay, the hydrogen's back, the methyl group's forward, the bromine's pointing up, and the ethyl group's here. Okay, so now we have a mirror image, but are they superimposable? There's 4 different things there. And if we were to rotate this around, not that. If we rotate this around 120 degrees, so the ethyl group lines up with the carbon, lines up with the bromine, so all of these line up, we'd have to actually have the hydrogen come out and the methyl group go back. So that means we'd have a hydrogen here and a methyl group here. So it's not superimposable. So that means this is one enantiomer, one of the pair of enantiomers. Enantiomers always come in pairs. And this is the other one. Okay. Now, look here, we have 2 methyl groups here. That means when we rotate it around, they will be superimposable. It does not have 4 things on it. It is not a chiral molecule. It does not have an enantiomer. Okay, it's the exact same molecule. Okay, so does that mean that all things with 4 different things bonded to it are chiral? Not necessarily, because we have to look for what we call a plane of symmetry. If there's any place in a molecule you can draw a mirror and it's the same on both sides of the mirror, it is not chiral. Okay, so let's do that example here, and we're going to see that in, especially when we have more than one chiral center, we can do this thing where we put a mirror here, and look, the methyl group here mirrors this methyl group. Half of this hydrogen mirrors half that hydrogen. half of this chlorine, there's half that chlorine. So because these look identical on both sides, this is not a chiral molecule. Okay, but all we have to do is add a CH2 to this side here, and it's no longer the same. Once it's no longer the same, it is a chiral molecule because the CH3 and the CH2 are not the same. CH3 and C2H5, sorry, the ethyl group is not the same as the methyl group, and therefore it's different. It is a chiral compound. All right. So how do we find stereogenic centers? Number one, find a carbon with 4 different groups bonded to it. Okay. 4 different groups, not necessarily atoms, but 4 different groups. So in the case here, we actually have 4 different halogens bonded to this carbon, so it must be chiral. Okay, here we have a CH2, an ethyl group, a propyl group, a bromine, and a hydrogen. That's 4 different groups. That means it has a stereocenter. Okay, so that's the first requirement. Okay, so let's look at this molecule and go ahead and unmic or turn your mics on, and let's look at all the different atoms and see which are stereocenters and which aren't stereocenters. Okay, so let's look at carbon number 1. It has 3 hydrogens on it. Is it chiral? Yes or no? Anybody? In the chat. Come on, there's 14 of us. Okay, yes, it is not chiral because there's 3 hydrogens on it. That's 3 different, those aren't 3 different things, so therefore it is not chiral. Let's look at number 2. Again, 3 hydrogens on it. Okay. All right, so no, it is also not chiral because there's 3 hydrogens on it. Well, okay, let's get this one. Let's look at this one real carefully. We have a nitrogen here. We have a C double bond C on this side. We have a C with a hydrogen and bonded to 2 carbons. Oh, wait, hold it. We're not showing this, but there's a hydrogen here. So we have a nitrogen, we have a C double bonded C, we have a C single bonded C, and we have a hydrogen. Is it chiral? Yes, because those different kinds of carbons count as different groups. It is chiral. So number 3 is chiral. So let's look at number 4. We have a C double bond O, a C double bond C bonded to an O. We have a carbon bonded to an oxygen, and we have a carbon bonded to a carbon. Okay, so those are all different. This is a C double bond C, C double bond C. This is a C double bond O. This is a C bond O, and this is a C bond, single bonds here. So 4 is chiral as well. See how we're looking for those different groups? Even though they're a ring, they're constrained, they still count as different groups. All right, so that's 4. Let's look at 5 right here. Oh, that should be fairly simple because we have 3 hydrogens on it. Not chiral, not chiral, not chiral. Yes, chiral, yes, chiral. All right, 6, we have C double bond C, C no double bond, an O, and a C. So yes, 6 is chiral. Let's see, we have C double bond C, CH2, CO, and those are different. And then of course, we have a hydrogen here. So 7 is going to be chiral too. Is 8 chiral? When in doubt, draw it out. Draw out your hydrogens. We have 2 hydrogens on that carbon. It is not chiral. 9 is chiral because this carbon is different than that carbon right there. So if we look at the answers here, we see that 1 and 2 are not chiral. 3 and 4 are chiral. 5 is not chiral. 6 and 7 are chiral. 8 is not chiral, but 9 is chiral. So part of the exercise that you're going to do as the activity here is to, number 1, the first thing you do is say, are there 4 different things? If there aren't 4 different things, you're done. Second thing you're going to do is you're going to look at that thing and say, oh, there's a whole bunch of different carbons here. Do any of those carbons have 4 different things? And if they do, that's the one you need to figure out, which is what kind of chirality it has, whether it's one form or the other form. Okay, so count 4 different things, and if it doesn't have 4 different things, move along. When doing mirror image, is the mirror always vertical, or can we do horizontal as well, if it makes sense? That is a great question. You can actually do the mirror in any way you see fit, as long as you do it from, what I'm going to show you is another technique where you build your mirror out from one side to the other, and you just do it the same way every time. It doesn't matter where the mirror is. Sometimes it actually makes sense. For example, when we have cyclic compounds like cyclohexanes, it makes sense to actually do the mirror below, because then you can see it flipping over and it looks more like whether or not it can be done. But yes, you can do your mirror anywhere you're going to see it. Okay, so now how do we draw enantiomers? And this goes to the question where can we do carbon 6 again? All right, let's look at carbon 6 here. Let's erase the stuff. Erase carbon 6. Okay, so if we look at carbon 6 here, we have a C double bond C bonded to a C. We have this, which is a C, 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 and bonded to an H. We have an O, and then we have a C with 3 H's. Okay, so when you look at that, this carbon is different than that carbon because of the double bonds. This carbon is different than that carbon because of the hydrogens. And this is an oxygen, which is different than all the other carbons. So that means that 6 must be chiral. Okay, great. All right, so let's talk about mirror images and how to draw our enantiomers. If you do it the same way every time, you can draw it any way you want. It can be above or below. Sometimes on exams, again, drawing it vertically is actually easier, but I will show you both ways to do it right here. And so what we're going to do is we're going to take any structure. In fact, I'm going to switch over to other items, blank. All right, so what we're going to do is everybody get a piece of paper out and we're going to look at this. All right, I'm going to draw a compound, and I'm going to do it this way. I'm going to say this is 1, this is 2. Our wedge out here is coming out toward us is 3, and then our dashed wedge is 4. Okay, now I want to show you how to draw the enantiomer. Okay, this is one of the structures. We have to draw a non-superimposable mirror image. So I'm going to draw 2 mirrors, one here and one here, to show you both ways to do it. And what we're going to do is we're going to start from the mirror first, and we're going to say, okay, this 4 is going to have the exact same type of bond it had in the mirror image. So it's going to have a dashed wedge. This 3 is going to have a solid wedge. Okay, the 1 is going to be straight up and be a no wedge. And then our other 2 over here is also no wedge right here. We've just drawn our mirror image. Okay, now let's try that again, but down below. So if we do it the other way, we're going to do 3 and our solid wedge. We're going to do our dashed wedge 4. We're going to do our 1 up here and our 2 over here. Okay, so it doesn't matter which way you do it. The only thing that matters is you have to keep the closest things to the mirror close together and the furthest things from the mirror furthest apart. And you have to use the same bond type. Okay, so you can do it either way, vertically or horizontally. And as long as you follow that pattern, it will work. Okay. So that being said, let's go back to our oh, that's our other, that's the end there. All right. So whenever we draw our enantiomers, we want to use that same kind of structure here. We're going to take our structure, and notice all of these have to be in some kind of stereo structure. You have to have wedges and dashes. Okay, if you don't have wedges and dashes, then you can't get your stereochemistry right. You have to know what's facing out and what's facing back. Okay, now it's best to do it where you only have one of your one solid wedge and one of the dashed wedges and the other three atoms in the same plane. Okay, so these three atoms are all in the same plane. Okay, so that makes it easier because then you don't have to draw like 5 different kinds of wedges. You only have to draw the solid wedge and the dashed wedge. Okay, so that being said, what if you draw something and you're saying, oh, this seems to have 4 different things on it, but it doesn't. Okay, this happens in rings a lot. You have to double check your rings, okay, because this looks like a stereogenic center right here, but if you were to draw a mirror right here, this half and this half would look the same. In fact, if you tried to figure out which side's different, you would start out with this carbon saying, okay, we have this carbon here. So we have a CH2, a CH2, 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 if you're going around this way. But if you went around the other way, we have a CH2, 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 CH2. So actually it's identical going around both directions. So rings kind of play tricks on us a little time. So double check your rings, okay? Because there's 2 of the same groups, that means that they are not the same. Okay, now what happens if your ring is not the same on both sides? If your ring is not the same on both sides, then it can be done. Okay, so if we're looking at something like this, we see that there's a CH over here, and this is a CH2. They're different. It's chiral. Okay, all right, I'm gonna skip that and go to our labeling. Okay, so I said before that our stereoisomers are the same except for their name. Their prefix is going to be cis and trans, or we're going to use R and S. So how do we tell the difference between R and S? Okay, first of all, when we draw our enantiomers, one's going to be R and one's going to be S. Okay, but we have to know how to assign these. So we're going to assign these using the CIP rules, which is Calhoun-Ingle something with a P, I forgot. And what all we're doing is we have 4 rules. 4 rules that we use. We only use 3 of them most of the time, but there are 4 rules. Okay. The first rule is we look at the atomic number, the Z number. Okay, not the atomic mass, the Z number, the atomic number. Okay, because each of the elements has a unique atomic number. Okay. If you can assign a priority of 1 for the largest atomic number, 2 for the second, 3 for the third, and 4 for the fourth, you're done. You do not have to use the other rules. Okay. So in the case of our number 1 here, bromine's a higher Z number than oxygen, which is a higher Z number than carbon, which is a higher Z number than hydrogen. So hydrogen is usually always your last one. And if we look at that, we can say, okay, if we draw its mirror image right here, it's going to be, our numbers are going to be still in the same places. It's going to be still on the same atoms. Okay. Now, what happens if you get from the thing connected to your carbon, your chiral center that has the same Z number on both sides? Okay. Give me a minute. Resume recording. All right. So what if you have something that has the same Z number? Well, then you have to keep going out further and further. So in the case of this one, carbon has the same Z number as carbon, but we're going to look out further from this chiral center, which is the middle one here, and say this carbon has another carbon attached to it, and this carbon only has 3 hydrogens. Therefore, it's lower priority because the other group has a carbon attached to it. Okay, so that being said, That's our second rule. So we keep going out further and further and further until you find a difference. Okay, so what if you have a double bond? The carbons are both bonded to carbons. You count each bond to that Z element, okay? So in the case of here, we have one carbon bond, one hydrogen bond, and one hydrogen bond for the structure that is right here, okay? Now, all right, let me actually, that's true. So we have two hydrogens, one is here, and the carbon here, all right? So that carbon, the first carbon attached to this bond right here, has a hydrogen, and a carbon. Okay, now let's go and look at the other side. This carbon here has a carbon, a hydrogen for this, but it also has a second bond to carbon. So that means it has two bonds to carbon. Okay, so that has two bonds to carbon because of the double bond. So that means it's higher priority than the carbon that's only bound to one carbon. Okay, it's only bonded to carbon once. This is bonded to carbon twice, therefore it's higher priority. So that's rule number 3. Rule number 1 is Z number. If Z number solves your problem, you're done. If they're attached to the same atoms, then you have to keep going out until there's a difference. If you have a double bond or triple bond, you count the Z number of that element for each bond. So for example, if you had this right here, and this was your chiral center here, you would say this is a carbon bonded to an oxygen and bonded to an oxygen. So you would count both of those bonds to oxygen, okay? So you were looking at that, okay? So that's rule number 3. So that only works for double and triple bonds. If you don't have double or triple bonds, you go back to rule number 2. All right, so, and then our last rule is if you have isotopes, the heavier isotope is the higher priority. Okay, we don't use this very often, but the heavier isotope is always priority. Remember, the only difference in isotopes is it's the same Z number, it's a different atomic mass. That's why rule number 1 says Z number and not atomic mass. Rule 4 is same Z number, but different atomic mass. Okay, so that's how the 4 rules we need to assign priority. So once we assign priority, we have to figure out how to say, okay, if I have my priority assigned now, I know how to do that. I'm going to figure out whether this is an R or an S. What does the R and S mean anyway? That's kind of weird, okay? So in the case of R and S, we're going to look at which way the priority goes. And what I like to always do is I like to put our lowest priority away from us and our highest priorities or our other priority groups next to us so that we can look down the axis of the lowest priority bond. Okay, why? Because we want to make sure that 1, 2, and 3 are going either in a clockwise fashion or in a counterclockwise fashion. Okay, so if they're going in a clockwise fashion, we call this rectus or right. And that is going to be giving us our R configuration. So all that means is when we assign our 1, 2, and 3, if we're looking at it here, 1, 2, and 3, we're going around in a clockwise fashion here. That's going to be our R or our rectus. Okay. Now, where's 4? Oh, 4 is back here. We have to look down that axis for 4, right? So we have 1, 2, and 3 going in a clockwise fashion. That gives us R. What if they're the other way around? What if it's 1, 2, 3, and we're going counterclockwise? Well, that is our S configuration, our sinister or left configuration. Okay, don't get mad, it's just very old nomenclature. But so the thing is, we're looking here is clockwise is R, counterclockwise is S. Okay, so let's look at this. There are several different ways to do this. Okay, I like to use my hand because I can take it everywhere. Okay, so what I always do is I try to figure out the orientation by using my hand. You can use either hand for this. So in this top corner here, what I'm going to do is I'm going to orient my hand such that the wrist is always my lowest priority. So this is lowest priority, okay? So in the case of this molecule here, 4 is facing at us. 1 would be my middle finger, 2 would be my index finger, and 3 would be my thumb, okay? Can I do R and S yet? No, I have to be looking down the lowest priority. So I need to rotate that around to look at me. And if I rotate that around and I'm looking down my lowest priority, we had 1, 2, 3, 1, 2, 3, and that is going in a clockwise fashion, okay? So that is R, okay? That's one way to do it. There's another way to do it called the pinwheel, which is you actually redraw the structure such that you've rotated it around. And sometimes people like that. And if we do that, we rotate it around. So the 4 is on the back now. All we've done is rotate it around by 120 degrees. So now we can see our 1 here and our 2 here and our 3 here. And it's going in a clockwise fashion, which means it is R. Okay. So pick one way to do it and then do that very well. If neither one of these methods works for you, go to myorganicchemistrytutor.com on YouTube. He has a thing called the pinwheel method. And if the pinwheel method works for you, do it. I really like my hand method because it's really fun to watch you guys do it when you're in the taking the exam. No, I'm kidding. It just works really well for me. Okay, so let's take a look at these two enantiomers and see if we can figure out which one's the R and which one's the S. Okay, I'm going to use my hand method again. We're looking at enantiomer A, and we have 4 is going to be my wrist. 1 is going to be my middle finger. 2 is going to be my index finger, and 3 is going to be there, but I have to rotate it around to look down to that axis. And so I have middle finger, index finger, thumb, middle finger, index finger, thumb. That is clockwise. So I think this is the R enantiomer. Okay, but let's prove it. Let's look at our other enantiomer. Our other enantiomer is going to be the one where we drew the mirror image of it. In this case here, 4 is already facing back from us, so we don't have to use our hand. All we have to do is say 1's here, 2's here, 3's here, and that is going counterclockwise. So that makes this the S isomer. Okay, so B is the S isomer and A is the. Do we see that if you looked at this, all you did was swap these two groups here to give us our different isomers? All right, so let's review the R and the S. Z number first, keep going out until you find a difference. Point the lowest priority group, always number 4, and it's usually hydrogen, away from you and determine whether it's clockwise or counterclockwise. All right, let's pull up the activity that I have emailed to you. And let's see, right here. Oh, yeah. Let me share my screen. Stop. And share screen. Adobe Acrobat. Okay, so you should be able to see my screen here. It's got the, again, don't do the second page. This is what we're going to do later when we're talking about E and Z. But for now, we're going to look at just this first page. Okay, here's your instructions. Number 1, are there 4 different things attached to the carbon? If the answer is no, then it's achiral. Move on. Are there more than one carbon? Yes. Okay, well, find the one that has 4 different things. That's the one you have to assign as R or S. Okay, now look at your, we don't have any isomers, so you only have to use the 3 rules. And we do have double bonds, but you might want to draw out your structures there. There's at least 2 of these, 3 of these that have double bonds that might not look like double bonds. So you might want to draw those out. Okay, and then once you have those, you have to assign it as R or S or A. A means achiral. Okay, then just take a picture of that and upload it to Canvas before midnight tonight. Okay. All right, questions on the assignment? Okay, so that being said, let me switch back to my slides. stop sharing and screen share via cable. Where are we? There we are. All right. All right, we're back to my slides now. All right. So that being said, you should be able to do all of that homework with what we've seen up to now. And what we'll do here is we will not do any multiple stereocenters on the exam tomorrow. We're just going to do R and S. So know what chiral is, know what enantiomers are, know what R and S is, and be able to assign R and S for the exam tomorrow. Okay, so what I'm going to do is I'm going to go ahead and stop here and answer any questions you have, and then we will prepare for tomorrow's exam. It'll be a little longer. It's going to be about 30 to 35 questions, and it'll have multiple choice and fill in the blank answers. Okay, so and then we'll continue with multiple stereocenters on Monday, and then I'll also give back our exams, hopefully live in person. I will update you over the weekend if things are not going as fast, healing as fast as I hope to. Okay. All right. Let me go ahead and stop sharing and open the mic to anybody who wants to talk. If you don't, go ahead and finish your the chapter 5 homework up to R&S assignments. Do not worry about multiple. Actually, don't turn in the chapter 5 homework until after Monday. I will reassign that as there, but you should do at least practicing R&S assignments for the exam tomorrow. Okay. And then we'll pick up on the rest of that on Monday. But definitely learn R&S, enantiomers, mirror plane, and the 4 priorities that required to do your priority list. All right, I'm going to go ahead and stop recording.